Great. Okay, so that's off-policy methods, right? Now, off-policy methods are using your past data. You can use data from other sources, but you're still, in some sense, they're often referred to as model-free, because they're not really like building a model of how the world transitions, right? And so I think it's a bit of a controversial point. But these Q-learning methods, they're building a model of future rewards, but they're not really building a model of how states evolve. And so they're often referred to as model free. I think they're actually more model based, but we'll kind of talk about why that is. But the point here is that it lowered variance and was off policy, right? And so if we look at the pros and cons of these methods, on policy methods are typically more performant. Like if you have tons of data, you have a simulator, use PPO, it will work better, right? In most cases. But off-policy methods are sample efficient enough for domains where you have limited data. So if I want to do RL on a robot, I would do SAC much more than I would do PPO. You can learn from images if you make some, like, some of the groups yesterday had some great suggestions on how to learn from images. And you can learn from like prior data. So if you have like data from prior experiments, like off-policy data that is suboptimal, like it's much easier to use it in an off-policy method than a PPO policy graded style method. Right? So if you're ever thinking about when to use which method, try to think about domains where these things are constraints, like you have lots of off-policy data which might be suboptimal, or you need sample efficiency. This is the right algorithm to use. If you're just going for pure performance in a simulator, use PPO. It'll work the best. And so if you're a practitioner, that's useful. That's useful guidelines, right? Okay, so what we're going to talk about today is we're going to start by thinking about what is the basic structure of a model-based algorithm. Then we'll start instantiating our first version, which is random shooting plus model predictive control. Then we'll talk about our second version, which is something called model predictive path integral. Then we'll talk about how to incorporate uncertainty. Then we'll talk about policy optimization. And then we'll talk about latent space models. And we are definitely not going to finish all of this in time, but we will, again, get as far as we can. Cool. So when I say model-based style, what do I mean, right? So if I think about an RL algorithm, they're trying to maximize the expected sum of rewards. We talked about our first type of method, which is gradient ascent. Let's take that objective to gradient ascent on theta, right? And everything like PPO and PG, they're all like little variants on gradient ascent, right? But they're basically just doing optimization directly on that. The second type of method we talked about was dynamic programming, right? Which is trying to build estimates of that thing using dynamic programming and then do gradient ascent, right? The third type of thing which we're going to talk about today is a method I'd call model-based optimization. And it's not only useful for RL, it's a general class of methods when you have like some non-differentiable model that you cannot take gradients through. You often use a model-based optimization method, which means that you learn a differentiable surrogate for that problem and then use that for optimization. Right? So like it's useful in lots of problems in science, lots of problems in engineering. Like if you have a non-differentiable system, you learn a differentiable surrogate, and then you try to use that for optimization. So if you can take samples from something, but you don't know its functional form, and you don't know like how to take gradients through it, this is a useful technique. So we're going to kind of study model-based optimization today. Okay? And so if you remember go ahead. Example of the distribution. So like, for instance, like one thing that some people look at is like protein design type problems. I don't know enough to say anything very smart about it, but in protein design type problems, you have like some knobs you tune, and then you have like a forward physical process that is hard to like differentiate, but you can get lots of samples for it. And so what you do is you try to learn like a differentiable surrogate, and then you say, I want certain properties out of my molecules. How do I change my inputs? Or like the same for material design. Kind of. So I'm sure lots of you work on other examples where this is useful. But the basic idea is if you revisit the definition of our MDP, right? And the MDP has a state space and action space for the transition dynamics, which is telling me if I was like at state ST, how do I transition to the state ST+1 on taking action AT, right? So this was the transition dynamics. The idea of model-based RL is like, we don't know this function, but we can get samples from this function. Let's try to use that data in order to learn like a surrogate to this function. And then we're going to use that as essentially a simulator or an approximation of the world, right? And so you're trying to take your world that you don't know, but you can sample from, and you're going to try and learn a model that is a surrogate for this. And you can learn it from not just on policy data. The nice part about model-based RL is off policy, it can be offline. But instead of trying to, in all of the previous methods, we were trying to get policies, right? And so we try to learn policies. We try to learn Q functions and then learn policies. In model-based RL, we're instead going to try and learn the dynamics. And once we learn the dynamics, we're going to try and use the dynamics model. We're going to pretend that our dynamics model was the true environment, and then do optimization against this model, right? So when I say a surrogate, what I'm going to say is that like this objective has a little bit of a shorthand. It's expectation under the true dynamics of your system. What you're effectively going to do is try and learn a surrogate to this, and then try to do something that looks like optimizing this in p hat, right? So it's a surrogate for your problem. And so the trick is that in model-based RL, you're optimizing under like an approximation. You just got to make sure that optimizing this approximation actually optimizes. Okay, so that's the key idea of model-based RL, right? You're gonna not try to approximate your policy or your Q function directly on real data. Instead, you're going to take an intermediate step. You're going to approximate your transition dynamics, and then you're going to use that to improve your behavior. Yeah. Okay. So intuition is like learning a simulator. You'll often call this world models. Like they're all kind of the same, right? They're all just saying that you're learning an approximation of how the world works and then planning it. Okay. So why would we do this, right? Like we don't care about models. Like nobody cares how the world works. We only care about acting in the world, or some people do, but I don't. I only care about acting in the world. So how do we do that? Or why would we do this? The first reason is to be adaptive and to transfer, right? So if I know how the world works more generally, I can use that same model to optimize many different problems. But if you look at like something like policy gradient, if you just directly optimize that objective for one reward, like it's inherently tied to the particular reward that you're optimizing. The same thing with the Q function. Like if you look at the policy that maximizes this, it obviously depends on R. If you look at the Q function, which is the expected sum of rewards, so some S and A under some policy, like it depends on R, right? Now you change the R, your Q function is invalid. And so, whereas with the dynamics model, like this thing doesn't depend on R, right? So it's agnostic to R, which means that you should be able to swap it out with the new reward function and still do reasonably well. And so one of the things that I find most compelling about model-based RL is that it lets you transfer across problems and be adaptive. One of the reasons that people often cite for model-based RL is efficiency. So there's some reasons why it should be efficient. Like the first reason is that it's inherently off policy, right? You can like learn from all of your prior data because all of it is telling you how the world works. As long as the world is not changing, it's telling you how the world works. And it's even a little hard to see. That is model-based RL, and that is model-free RL. This is one of my good friends from grad school. She had this paper where she was doing RL on like a robotic hand, and you can see that it's orders of magnitude faster there. I think we're still figuring out why that is. I don't know if we have a super clear reason for it. But one argument is that if I'm supervising on rewards, it's a much sparser signal than if you're supervising on state. Right? So you're saying like, I can tell you like the state is a rich signal of how the world changes. The reward may be zero everywhere. And so it's not a very rich signal of like how the world changes. So that's one argument for model-based RL.
Is there rewards or why?
The rewards or returns are y-axis, yeah. Or success. No, but yeah, I think that's return. And the last is that it's kind of simple in the sense that okay, there's this like complicated dynamic programming procedure, and this thing was I said it's not gradient descent, and it may or may not converge, and all of this stuff, right? Whereas model-based RL is supervised learning, and so it's simple. And so all of the nice benefits that we have from supervised learning might translate well into model-based stuff. I'm not sure. That's why there's no lecture. Um, so the other natural benefit is that it's off policy. Let's see your answer to Kunal's question is that because it's simple, like basically the challenge comes from like when you optimize this problem with a learned model, like approximations in p hat basically cascade to get worse and worse and worse. And so optimizing this objective may not actually optimize your true problem. And so two things that make it hard. Often learning p hat is hard. And second, optimizing under a learned p hat can be hard. And we'll talk about those in a second.
Sorry, guys.
Okay. Any questions before we keep going?
I have a question.
Yeah.
Is this related to system identification?
Yeah. So you can think of model-based RL as, you can think of system identification as model-based RL under a very particular model class. Right, so system identification says, okay, my model class is going to be like physics, and I'm going to or it's going to be the manipulator equation. I'm going to identify the mass matrix and the inertia and like friction. Whereas in model-based RL, often you like don't impose as strict of a model class on there. You like say you have a neural net that goes from images and actions to next images. And so system ID, but not forced into a parametric model class. Right. So you can think of system ID as like model-based RL for specific model classes.
So it's doing also prediction.
Yeah, so like the nice part about system ID is that often like let's say you're using a physics simulator, right? And you're doing like collecting real data, you're identifying the parameters. Physics simulators naturally obey certain properties, like they naturally obey conservation of momentum or conservation of energy. Whereas if I just learn a model, it may not. Right? And so, but the challenge is that unless you have a differentiable simulator or something like that, then system ID can be hard. Whereas model-based RL can just be really this. So they're very connected. It's just about the choice of model class. And Dima works on this a bunch, right? So you could tell us more about are there other things that you find to be different between system ID and model-based RL?
I feel like you described it pretty well, like what is kind of
Yeah. I think system ID can be unreasonably effective often because your model class will extrapolate, where often models that you learn neural net style don't extrapolate the same way. Okay. Sweet. And then you can come up with nice videos. So this is like some videos from a model-based algorithm that's trained to like rotate these balls in hand with just 2 hours of real robot training on the shadow hand. Fun story is that it like broke. So they had to fly in some engineers from London to fix the hand. And so it was a fun experiment. But like with the model-free RL algorithm, at least at the time, it would take orders of magnitude longer. Cool. So that's why I think we should do it. The reason I find most compelling is the transfer reason, but lots of people think about it for different reasons. So the general problem statement is that we're going to learn a model which approximates the world. So we're going to try and minimize some loss functions. So we're going to collect some data. We're going to try and find the parameters of our loss function, or parameters of our model that minimize the loss function. And we'll talk about what the loss function will be. Different loss functions lead to different algorithms. And then you'll do what you often refer to as planning, right? I think planning is a bit of an overloaded word, but the way I think of it is that if you have a surrogate model p hat, you're just trying to decide how to act in that model p hat. Using some policy file, right? Oftentimes in model-based RL, you don't have to find a policy. You can also just find a sequence of actions. And so the idea behind like model-free RL in some sense, you collected a bunch of data, right? And then you like got this like pie. It's fully parametric. So you got this pie. Now you can throw away your data. Like all you need is your pie. In model-based RL, what you do is you got this data, and then you learned a model p hat, and then you do a lot of test time planning. in many model-based RL algorithms, which means that like there's two types of model-based RL algorithms. One which tries to solve, it just first learns this p hat, then tries to optimize this, then throws away the model and just uses the policy. There's another type of model-based algorithm that says, let's keep around p hat and do more computation at test time. Okay? What that means is that at test time, I'm going to be at a particular state. I'm going to try and imagine what the future was using p hat. And I don't need to like imagine all possible futures. I just need to say how to act in my current state. Right. And so the benefit of doing test time computation is that I don't need to be globally optimal. I just need to be optimal here. Right. And so another nice way of thinking about model-based RL versus model-free RL is it shifts when you do your compute. And so for those of you who are thinking about LLM problems, often you'll do like test time computation, like O1 or whatever, is like trying to do more model-based RL at test time because it's doing more planning at test time. Whereas just doing like direct inference or decoding is kind of like more model-free or more imitation. Because it's like, it's not saying that you have to be good on every instance, you just have to be good on this instance. Okay, does that make sense? Okay. Cool. So that's the general problem statement. And the question is, how should we instantiate like I've left a lot of open questions. How do we solve that optimization? How do we instantiate the loss function? How do we, the question Kunal is asking is like, why shouldn't we do this all the time? And that's what we try to cover. What we won't cover is we won't talk about ILQ or ILQG. Byron does a great job of covering that. We won't talk about nonlinear trajectory optimization, which is basically the version of this where you like know the model and you know gradients to the model, but it's nonlinear. And we won't cover shallower classes of models. We'll mostly cover models as neural nets. We won't cover GPs and other non-parametric. They're all great. They all have their benefits. That's just not what we're going to cover today. Go look at Byron's lectures. They're great. Okay, so what we will cover is we're going to use neural networks as our model, which means that we're going to try and use neural networks. And so both of these examples are with neural networks as our model. So the bottom is some of Byron's work on auto rally, where they're trying to drive a car on a dirt track really fast, which is hard to model analytically, but they learn a model to do it with some data. And so we're going to try and show you how neural nets can be useful for these problems. Okay, so the assumptions we're going to make. The first is we are not going to assume access to known dynamics. We're going to assume the access to the ability to sample from the dynamic, which means that I can draw samples from P. I am not told the functional form of P. I don't know the gradients through P. Right? We assume that you can reset the environment, so you can keep resetting the environment and collecting more data. You assume that the reward function is known. So like the reward function in model-free RL, we didn't assume was known. We assumed that the reward function was provided to us as we acted in the world. So we did S prime and we got an R. So we got a scalar. Here, what I'm going to assume is that we know a function R is a function of S. And it's like a function that I can evaluate anywhere. I have access to the functional form. So it's like VLM or something, or someone has written some code to give me a reward function. For now, let's just assume that we have that. We can also learn it. Yeah.
Are we also assuming that we know the form of the reward function?
Yeah. I'm not in the example I'm going to talk about today. We're not going to actually take gradients through it. So we don't actually need to know its form. It's more like the reason you're going to need it is because you're going to hallucinate futures, and you need to know how to evaluate those hallucinated futures. So we're going to have something that can tell us what our rewards are going to be in the future. And then next lecture, we'll talk about how to get rewards. Okay, so inverse order. Okay, so those are the assumptions. Okay. And the basic template of an algorithm we're going to have is we're going to collect some data. We're going to learn a model. We're then going to do planning. We're going to go back and collect more data. Right? So it's very similar to off-policy RL in a way. But in off-policy RL, we collected data, we learned a queue, we updated the policy, we repeat. Right? Here, what we're going to do is we're going to just learn a model, and then we're not going to explicitly get a policy. We're just going to do this planning procedure to figure out how to act. We're going to go back, use the planner to collect more data, and go back, collect more data, update your model, and repeat. Right? And so we're going to try and figure out what each of these steps are. Well, data collection is just standard, but we're going to try and instantiate model learning and planning concretely. Right? But when I'm going to talk about model-based RL, it's still an online algorithm, but it's going to be off policy. So we're going to collect a bunch of data, throw it into a replay buffer as we've been doing. We're going to use that to learn a model. We'll talk about how. And we're going to use the learned model to kind of like do planning. And planning is your policy. Right? So it's saying that like anytime, unlike Q-learning or policy gradient, you're not like trying to get an explicit policy. You're just trying to say like, let me figure out how to best act using my model of the world. And that is the action that I will take in the world. And then you like take actions that way. You collect data. Your model might be wrong. You're going to go update your model. Yeah.
Quick question on this. What's the difference between this and the like approaches like gradient optimization?
Again, I think it's a question of like how much structure you want to assume. Right? So like I guess Bayesian optimization, you often assume like an acquisition function, and you'll assume like a kernel. Like whereas here it's largely like you're assuming data and you're assuming a really rich expressive policy class. And then the thought is that so the reason that's important is because you can scale the dimensionality of parameters that you're optimizing. So I think BO is like really effective in small parameter spaces and when you know things about the problem. But for instance, for robotics, it's like you have like a large set of parameters that you're optimizing. So and you go from perception. And so in those cases. Okay, sweet. So that is the general anatomy of a model-based algorithm. Let's start instantiating these pieces. So what is model learning? Well, model learning, we're going to take the same recipe we did for imitation learning. We're just going to do maximum likelihood, right? You can call this next token prediction. You can call this supervised learning, whatever you want to call it, right? It's just doing maximum likelihood, which is saying, try to learn the parameters of a function that take in S, take in A, and try to predict S prime, such that the like actually executed S primes in the world were as high likelihood as possible. Okay. And so that's going to be our model learning procedure. And we're going to start by instantiating planning with random search, right? So random search is basically try a bunch of random stuff and pick the best of the random stuff and execute it, right? And so it's like the most naive search procedure. So we'll start with that and then we'll make it better. So let's start by thinking about what model learning looks like, right? So maximum likelihood is, you'll notice here that we're fitting a one-step model, which means that I'm not fitting multiple steps into the future. I'm fitting one step, which is saying that I'm at S, I take A, and I like want to figure out what S prime I go to, right? And so I'm going to choose a class of models, P theta hat, and I'm just going to learn a bunch of one-step models with supervised learning. Now, the interesting part here is that like different choice of models or different choice of P theta hat will lead to like different types of models, right? So, or different types of loss functions. So for instance, if you choose P theta hat to be a Gaussian, right, then like that objective becomes mean squared error. So for those of you who like think of model learning as like, you try to do like S prime minus some F of SA, right? And you try to like minimize this with respect to F, you can derive this by just doing maximum likelihood with P theta hat as a Gaussian. And try to think of it as like P theta hat is like some X of like S prime minus F of SA the whole squared, and you can like derive it. But like, why might that not be enough? Like, why is a Gaussian not enough? Yeah. Multimodal. Multimodal. So when are dynamics multimodal? Like, what are examples of multimodal dynamics? Because with policies, it's like, okay, I can go left or right. But like, where does multimodal dynamics come from? The dynamics is how the world works, right? So yeah,
Maybe you're like rolling it's
uh-huh. Yeah, I guess that, yeah.
I mean also maybe if you're throwing a bat,
Yeah. Makes sense. There's like certain stochastic events that could happen. You could also have like, for instance, humans be part of your dynamics and you don't observe their full internal state when they're stochastic. Right? I always find an interesting way to think about multimodality and stochasticity is it's like, it's because of unmodeled effects, right? And so anytime you have like any unmodeled effects, like they often manifest as stochasticity. If I knew the human internal state perfectly well and they assume they're like roughly rational, I could like simulate this deterministically, but often this partial observability often leads to stochasticity. And so that's one way of thinking about it. But yeah, you could change p theta hat to be an energy-based model, and then your maximum likelihood procedure becomes something called contrastive divergence. You could do diffusion modeling, and this thing becomes you like would train with the objective like score matching. Score matching is not exactly maximum likelihood, but you could show that it's quite related. But point I'm trying to make is we're going to learn one-step models, but you could use any of these model classes. They lead to different behaviors. Yeah.
Like one-step diffusion?
Yeah, you can still have it's a conditional diffusion model, right? So it's a conditional diffusion model that takes an S and A and then models a distribution over S primes. Okay, good. So that is model learning. So we did that. The trade-off here is that more expressive models potentially overfit more in the low data regime, right? So system ID is nice in the low data regime because it overfits less, but more expressive models, you need more and more data.
What is D?
D is a data set. D is like the same thing you did in off policy RL, is all the data you've collected thus far. It's an arbitrary off policy data set, right? So it's saying that it's like you sample data in the environment, either from your past iterates or from somewhere else. And it is all that it has to be is that it has to be sampled from the same dynamics.
So wouldn't our model depend on our policy?
Your model, so it depends on your policy in the sense that it's like good in places where policy is high likelihood and bad in places where it's not. But like, for instance, imagine that like, because your model is P of S comma A, P of S prime given S comma, sorry, if S prime given S comma A, right? There's no policy dependence, but it's one step and the action is going in, right? So it's like irrespective of where, it's kind of the same logic as Q learning. It's like irrespective of where A came from, which will come from any policy, this is like a fundamental property of the environment. Right? Like certainly, like I think on a technical point, like imagine that you had like data coverage here, your model will be accurate here and maybe inaccurate here. But I think that it's inherently agnostic to your policy because you're taking in the action that you play. Right? And it's like a fundamental property of your environment. Now you could think about like multi-step models, and multi-step models start to become dependent on your policy. Yeah. So for instance, you could consider a model of like what is PST plus K of ST and AT under the policy phi, then it's inherently dependent on your policy. But if it's a one-step thing, it's like a property of your environment. Okay. Cool. That makes sense, Rob? Following? So that's how we do model learning, right? One like practical trick that often helps a lot is to like, instead of learning S prime, learn the residual. And it like lowers variance a lot. And it just like, in most practical model-based algorithms, you would learn something like the residual rather than just prime. Okay, so now we've trained our model, we've taken our data, we've trained this model, and we have P theta hat. What do we do with it? What's the simplest thing we do? So rather than modeling, so right now what we're doing is I've said do maximum likelihood on S prime given SA. You can do maximum likelihood on S prime minus S given SA. The model the residual, right? And then to get the actual next state, what you would do is you would sample from this distribution and then just add S to it. Right? So you like model the residual, you model the distribution of the residuals, and then you like to get the next state, you sample the residual, and then you add it to your current state. You still get a distribution over next state. So the thing you're modeling is the residual. Yeah,
Also, just to be clear, in model-based model, we're modeling the transition to the next state. Do we ever model the rewards collected during these transitions anywhere?
That's a good question. Yeah, I think it varies from implementation to implementation. Like the last algorithm we'll talk about, Dreamer, does do that. A lot of the like more shallow model-based algorithms, or I say shallow, I mean like not from images, often assume that it's given to you. But you could, right? You could just do the same objective But you could also add like a supervised learning objective on like R equivalents.
Yeah, so I guess the follow-up question is, if in model we don't actually model the rewards, then how do we plan?
So that's what I was saying with the assumption is that you're assuming that the reward function is given to you. So the functional form of the reward is given to you so you can evaluate hallucinate.
Sorry, I validating.
No, that's a good one. Good question. Okay, let's keep going. So we want to do planning. How do we do planning? Well, essentially planning often looks something like this, which is saying that you start at some current state S naught, let's call it S naught, and then you're going to act with some series of actions A naught to AP. Your states are going to transition according to your learned dynamics, right? And you're going to like find the sequence of actions that maximize the sum of rewards where the states are connected through the learned dynamics. Right? So this is given to you, like the reward function is given to you. This you've learned, and you're trying to find the maximum sequence of actions. Okay? So remember, unlike policy learning, policy grid, we're not trying to find a pi. You're just trying to find a sequence of actions. So it's kind of like one way of thinking about it is you're at this state as not. You're like imagining many possible futures, right? And then you're like picking the best one. Or I guess I haven't really prescribed how to optimize this yet. But the objective is trying to find the best possible sequence of actions such that if I play them under my current model, I get the highest possible goal. Okay. So what is the simplest way to do this? Yeah. Yeah, that's right. Just a random search. So you just like sample a bunch of random sequences and then you pick the sequence that give you the highest sum of rewards, right? So you just like sample n different sequences, you roll them forward through your model, you evaluate the rewards for each of those sequences, and then you pick the best one and then you execute, right? And so you like sample lots of different sequences. That was the best one, you execute that sequence. Okay, so that's the simplest thing we could do. Why might it have problems? Yeah.
Huge search space.
Huge search space. Yeah, okay. The huge search space. What are other problems?
In your successive iterations, you could be sampling 5 different strategies, so you could have a lot of jitter.
Are there other problems that we could have?
Model is not accurate.
Model is not accurate. So if you take like your model is wrong, right? Like it's like when you say something is a model, it's by definition wrong, right? And so it's wrong, which means that if you act pretending that the model was perfectly right, you might end up with the wrong sequence of actions, especially in a huge search space. And if you just play them open loop, then you like are likely to like you're likely to like see outcomes that are different than what you expected, right? If you're executing actions open loop, that's kind of the problems that you run into, right? So the fix to that is really simple, right? It's what you call model predictive control. And saying that even if you choose this set of things and you like run it, you might see something different than what you planned for. So let's even say you like solve the huge search space problem. You like got to the local optimum of your objective. Because your model is wrong, when you run it in the real world, you'll see deviations from where you wanted to go, right? So this is the point of feedback control generally. And so the idea here is that you can just do replanning, which means that you'll run it for a little bit and then you'll plan again. So you'll like choose the best path, you'll take a step along it, and then you'll plan again, right? And then you take a step along it, and then you plan again. Then take a step along it, and you plan again. And so the idea is that in many MPC is not optimal. So this technique is called model predictive control, or MPC. It's not optimal in all settings, but the idea is that even if you have a wrong model and imperfect search, as long as you're like replanning enough, you can recover from failures or recover from errors. Right? And so the idea is super simple, but like it's arguably one of the most important ideas in control, right? It's saying that like you just replan. You assume that your model is imperfect. There's going to be disturbances in your system, but you just keep replanning, keep getting feedback. And so that's all the first version of the algorithm is going to be. You plan the random shooting from ST, you execute the first action, you reach some new ST+1, it may be different from where you expected, but you go back and you replan, right? So you don't execute the whole sequence of actions, you execute the first action, and then you replan. Okay, why might this, well, like, what are the cons? Like, why shouldn't I do this all the time? Compute time. Other cons.
Only of training to get the policy.
Sorry,
Only of training to get the policy.
but that's a pro, right? So I'm asking for a con. Yeah, so like, why is this maybe not a good thing?
I think it's training.
Right, so random shooting is definitely bad, and we'll try to do better than random shooting. But I guess if we disentangle the ideas of random shooting, like maybe NPC is about just like doing iteration this way. So often what you'll do is you'll do like worse random shooting with the expectation that replanning will fix your errors. So the other problem that might be that you sacrifice global optimality. Right? So you're saying that like I have a worse controller, I might sacrifice global optimality. So that's usually okay in many problems. Okay, so the first version of the algorithm that we have is we collect a bunch of data. We learn a model with maximum likelihood, supervised learning. We do planning with MPC and random shooting. And then you like go back and you collect more data, right? So as you can see here, the way that this procedure is going to work, you're going to start by collecting a bunch of data. This data is going to learn a key. Then the way you like the planning and data collection loops are kind of like mixed together. Like planning happens during data collection. These are like kind of like mushed together. But in some sense, in this procedure, there's no policy. The policy is implicit in the planner, right? So you're saying that like, I'm going to be like executing my system. Let's say I'm at some particular state ST. If I want to figure out what action to take, I don't have a policy anymore. Instead, what I'm going to do is I'm going to run this procedure, random shooting. I'm going to pick the best sequence. I'm going to execute the first thing. That's my policy, right? And so the policy is not like a neural net. It is a procedure. But a policy is just some rule to map from your current state to the next.
Actually, when we're training our step, do we only run the planning or do we also try to update them on?
That is a great question. You can do both. From my experience, a lot of the algorithms that neural net model-based people do, they only update the model in batch. And they like run NPC only planning. And they collect data and then they update the model in batch and then do planning, collect the data, and repeat. But you could keep updating it as you're going. That's a good point. Okay, excellent. So that is version 1 of model-based startup, right? So it's saying that we just do MPC and shooting. And then you keep going. Okay, sorry. Good. Great. So any questions before we keep going? So question to ask is like, does this work, right? And
here, the swimmer performs a left turn.
this is from a few years ago, but basically they learned small neural network models from this like swimmer problem. It used to be a little hard at a point. But it's trying to follow those waypoints. So they learn a model from data, and then they do like planning with just random shooting. And it kind of works, right? The important thing to note here is they're not doing random shooting with full horizon. So if you look at the objective here, they're like capital P is like small. So they don't do full horizon planning. The idea is that I don't need to deal with all of the waypoints. I'll worry about that later. Let me just figure out how to get to the first one. And so it's like lazy. But the point is that we can kind of get it to work in sim and you can get it to work on real. So the system there is a little cockroach. But the cockroach is made of like extremely flimsy material, and that makes it really hard to build an analytical model of it. And so instead they just collected data by just like wiggling the cockroach around randomly. And then they use that to plan, right? And so I thought what was really amazing, well, I don't know, I was shocked when I saw this result. I guess it was in 2017 or 16 or something. But it was 20 minutes of training time. You do MPC with extremely short horizon with a neural network model and seems to work. So I think the fact that it can work on that cockroach is shocking. But it's pretty awesome. Okay, but you know, as I said, we have a whole lecture on this, so it can't be the answer, right? So if you look at how good model-based RL is, like the results that she had, like the model-based RL does not zero, but it's like far worse than an algorithm. Like I guess she was running TRPO, but PPO would do even better. It's like far worse than the asymptotic performance of a model-free algorithm. And so what we're going to try and do in the next couple of sections is try to get that performance better. And so there's a huge gap. And so what she did in that paper was she initialized the model-based RL and then fine-tuned the model-free RL. But I think we can make model-based RL better. So what we're going to do next is try to make, as she was saying earlier, that random shooting is a problem, right? So we need to make random shooting better. And so we're going to try and think about how to make random shooting better. So random shooting, as you probably noticed, is kind of like finding a needle in a haystack, right? You're like starting here, and you're saying that like, okay, this is my goal, or this is where I get reward, and I'm just gonna like hope, like by playing random actions through my model, that I'm gonna like get to the goal, right? So one thing that is important to notice is when I'm doing like random shooting, oftentimes you like sample actions from like a uniform distribution or a Gaussian distribution, which means that I'm going to like, it's like motor babbling. You're like playing random actions forward through your model, and you're hoping that random actions will lead you to something good, right? And so you do that on a humanoid, you'll be in trouble, right? And so there's this like needle in a haystack problem that gets worse with action space and gets worse with horizon. Okay? So like the longer you have to search in the future, the less likely a random walk is to get you there. And the bigger your action space, the less likely motor babbling is to get you there. And so we need to find a better search method. So given what we've studied so far, what is a better search method?
One policy to something like that.
Yeah. And we will. But before that, let's think about what a better search method might be for sampling-based methods. Right? So sampling-based methods are nice because they like, it's really simple. And I think we can do better than like random shooting with uniform motor babbling noise. What might be a little bit better, right? So like maybe think about it this way. If your goal is here, right now what's going to happen is that I'm going to like sample a bunch of stuff. And then if I like, let's say my reward wasn't completely sparse. Let's say I had like some signal on what is good, right? And I did like a bunch of sampling. The sampling is completely IID every time. So every time I want to do planning, I sample completely IID and I repeat, right? The logic that we could use is that as I like iteratively sample, I can improve my sampling distribution, right? So like right now I'm going to sample uniformly, and the next time I'll sample uniformly, and the next time I'll sample uniformly. But as I know what is good and what is bad, I should refine my sampling distribution, right? And so the logic behind this next set of methods, which is called MPPI, is basically just to refine your sampling distribution, right? And so the way that I like to think about it is that initially you're going to like do random shooting by sampling from a uniform distribution. Just going to throw random. It's kind of like when you're doing beam search and LLM, you also like, you can choose what distribution you're sampling from. This is often used in robotics, you'd sample from a uniform. Instead, we're going to inform our sampling distribution with our reports. And so if you go read the paper, it's like extremely dense, but here's the vibes that I got, which is just try to reweight your sampling distribution to be higher around to have higher likelihood around the things that have higher returns. So it's the same logic that we use in policy grade, right? We take things that are higher return and upweight them, things that are lower returns and downweight. Okay? And so that's all that MPPI is really going to be. It's going to say that let's upweight our sampling distribution around high return things and downweight it around low return things. And so all we're going to say is that we want to go from a uniform distribution like that. Let's say the first time we did something and this was like our best return, right? We want to like upweight things around here, downweight things around here. The next time we sample, it looks more like that. And then we do it again. And then the next time we sample, it looks even more like that. right? So you're defining your sampling distribution. You're still in planning, but you're defining it over every iteration using the reward function of the cost. And so the procedure looks as follows. You sample a bunch of action sequences from some distribution. Let's say it's your initial distribution. Then you run them forward through your model, right? So that's going to tell you what states these actions go to. So it's kind of like hallucinate the future under your current set of actions. Then you evaluate each of those sequences based on how good or bad they did. Right? So you look at what is the expected sum of rewards, and then you re-weight your sampling distribution to be higher along sequences that were higher reward and lower along sequences that were lower reward. So you just have you can kind of think of it as you take a bunch of action sequences, you weight each one of them by exponentiated sum of rewards, and then you refit a sampling distribution weighted by this exponential sum of rewards. Right? And so it's going to move the mean of your distribution closer to things that were higher reward. So earlier you were sampling maybe the Gaussian like that, and now you're going to sample a Gaussian which is closer to that. Right? So you're going to keep, and then you repeat this procedure. So, you repeat this procedure. So you replace PA by a better distribution.
He had on the bottom.
This thing? Yeah, I guess it's you. So that is an action distribution, not a state distribution. So you're reweighting your action distribution. So in effect, often what you'll do is you'll get do a weighted regression where you refit the mean weighted by the sum of you will sample some actions and you refit you do a weighted linear regression or weighted regression to fit the mean weighted by the sum of the words. So yeah, that's all that MPPI really is. There's some proofs that you can kind of come up with why this kind of distribution, optimal sampling distribution, and so on. But it's just in normal planning, what you do is you run things forward, you choose the best, you execute, you repeat, right? In MPPI, you have a little more, it's a little more compute intensive, but basically, let's say in the real world, you're at some state SC, and you're now dotted lines means hallucination, solid line means real world. So dotted lines are going to in random shooting, what you do is you do a bunch of dotted lines, you pick the best one and you'd execute it. What we're going to do here is we're going to do dotted lines, and then we're going to evaluate those hallucinations to see which ones are good. And then you're going to sample a more refined distribution still in hallucination. And then you refine it again and sample even more refined distribution and hallucination, and then you would execute, right? And so rather than just one round of planning, you would do multiple rounds of refining your sampling distribution, and then you would execute. So you can kind of think of it as you start spraying, right? And then you see which things work well, kind of refine around those, see which things work well, refine around those, and then you make a decision, right? And then you repeat. It's almost like a little mini RL procedure. Yeah.
So do we, each step that I'm gonna take, do we start them on a uniform distribution again and again?
That is a great question. Actually, don't know how. I think so in practice. No.
So in practice, one of the things, so this procedure that you described is I guess what you're saying is for every action output, you're doing that replanning using the separate distribution. One of the things you can do in practice is you can make the assumption that my control rate is so fast that my next state that I would be at, if I was to do one step of planning and then just act, is super similar to where I'm
See, so you can retain the previous guys.
Yeah, but you can also do something which is in practice what you do is you produce the sequence of actions, let's say A0 to AN, right? And then you execute A0, and then with MPC or MPPI, what you do is you shift everything by one step. If you execute A0, and you resample around the team, and the last thing I think.
But yeah, basically, you can choose the PA that you want, and I guess what Sid is saying is you retain the PA from previous states if they're closer. Just reason. Yeah, so that's what MPPI does, right? the basic scheme looks very similar. You like still do maximum likelihood. Then you go and do planning, but in planning, you don't do this one round of random shooting, you do this MPPI procedure. And you still do MPC, right? So MPC just refers to the fact that you will replan every so often. So you're going to do within every MPC step, you'll do MPPI, you'll execute, and then you'll replan, right? And then you're going to like kind of optimize an objective like this, go back, collect more data, and repeat. So the nice part about an objective like MPPI is that your rewards don't need to be differentiable. Your model doesn't even need to be differentiable. It just needs to be forward simulatable. The model doesn't even have to be learned. You can have it be not learned, right? But it's like a general procedure that works across lots of rewards and cost functions. So the reason why, like maybe some of you are thinking like, why not gradient descent, right? Why not gradient descent? If P hat is differentiable, R is differentiable, why not gradient descent or gradient descent? Because it allows for a broader class of reward functions and a broader class of models. And so one way of thinking about this is it's like very much RL-like. It's kind of RL, right? You like did some stuff, then you took the good stuff, you operated it, then you did it again and again and again. But you're not getting a policy, you're getting more of a sequence of actions. Okay. And then you execute it first, and you do it. Okay. Questions, thoughts, concerns?
Just like squiggly line diagram, just like real thing.
Uh-huh.
kind of sandwich it. That's like whole, like that whole area.
Yeah, so it's kind of like, I guess when you say full sheet, you mean like, don't just predict a point estimate, predict something like a distribution. Yeah, so that's the next thing we're going to do, which is like kind of predict like uncertainty estimates and propagate them. But yeah, that like often helps to predict like a distribution forward because you want to see like what average outcomes are good rather than what individual outcomes are good. So yeah, that's the next thing we'll cover is basically like predicting, like maintaining uncertainty in our models, and so we can predict like multiple futures. Great question. Okay. Here's some nice examples from Byron and friends. There's nicer examples from his newer experiments, but this is one I find compelling. Where they had like this dirt track, which is obviously really hard to model. And they use basically a version of MPPI on this, and works pretty well. I think they drove around the track a few times to build the model, and then they did planning with it. Yeah.
The reward here, like just doing the crash.
I actually don't.
The reward was speed, so actually more like speed and like stay at the center line as much as possible. Like don't crash, stay near the center.
Nice. All right, so that is P1, which is improving our sampling distribution from random shooting to MPPI. Okay. Now, what issues have we not talked about yet? Right. So going back to Kunal's question from earlier, like why not always just learn one-step models? Like what might be the problem with learning these one-step models with supervised learning? Problem we've talked about before, right? So in imitation learning, we talked about this problem. So what's the issue with learning one-step model? Compounding error, right? So the problem is that if you're learning one-step dynamics, rollouts under the model may not be rollouts under the environment, right? So the same thing as imitation learning, you learned like a one-step action, so you pretended the sequential problem was not a sequential problem, right? And so you often call this model bias or compounding error, but the idea is that if you learn a model and your model makes a little mistake, same as your imitation learning made a little mistake, you might have the error increase over the rollouts, right? So the point here is like, let's say you learned a one-step model. The one-step model loss is pretty low, but the multi-step model deviation is pretty high. Okay? And the interesting thing is this happens even for non-chaotic systems, right? It's like, even if your true system is not chaotic, but your function approximator, there's crazy things out of distribution, you'll see that like small errors will lead to like big deviation. Because your model class is unconstrained neural net, which like can lead to chaotic outcomes in the future. When I say chaos, I mean like small changes to the input lead to big changes in the output. Okay, so in general, you have this, it's a similar problem of compounding error. You start at some state S, you like made a little mistake. You like fed some A in. Let's say it's even a seen A, but you made a little bit of a mistake. Then you see a more unseen S prime, and you feed in seen A, but you'll get an even bigger mistake in the right? So two types of things can happen. One is because your model is has small errors and you have compounding error. And the two is that you're like trying to like do planning for actions that you haven't seen. Right? So like let's say I've only seen actions that go this way, and when I ask the model like what goes that way. It's just like a counterfactual question. But we're largely going to focus on like these little model errors and how they compound over time, right? And so if you have this lack of data, basically if your model makes a little bit of an error, like you have no idea how to recover from there. And so you have things going out of distribution and continue amplifying. Right? And if your model is bad on OOD fits, it can get worse and worse and worse. So what happens if I, like the reason this is bad, right, is like imagine that this was the true outcome, which is bad. And this is the imagined outcome, which is great. And now I'm going to take this action, which was, I'm going to like think this action is good when this action is really terrible. Right. And so you can like it can lead to controllers that are catastrophically bad because it's imagining a great future. And so when you have this model bias issue, that's also the issue. If you remember the cockroach videos, the reason they only did 10-step rollouts is basically the model matches the true model for like 10 steps and then starts deviating. So often with neural net models, you have really short rollouts because they only match with really short horizons. Okay. So most, at least this was true at least a couple of years ago, you could only roll them out for 5 to 10 steps. They've gotten better in the last year, but it's still generally a problem. So how can we deal with this? The first idea is let's just change the objective. Let's just change the objective, which is a one-step prediction error, to a multi-step prediction error, right? Which says that rather than doing maximum likelihood, you can kind of think of like you have some S and A, which leads to some S prime, or let's say a model predicts S prime hat. You take that and A prime, run it through your model again, and gives you S prime or S hat prime prime. You run it forward, and then you like minimize the loss on all of these, right? And so you're saying like you did earlier, you were doing one step loss. Now what you can do is you can recursively run your model. You can recursively run actions through your model, right? And then like minimize multi-step loss. Right? So you can think of this as like this objective is one step loss, right? So it's trying to say let's try to make S and A be as close to S prime as possible. And you can take the output of your model, stick it back into your model, and then predict the next step, and then supervise the losses at multiple steps, right? And what this is trying to do is trying to say like what the true environment was and what the multi-step model rollouts were need to be closer to each other, right? So like this needs to be as close as possible to each other. But this is often called equation error, and this is often called simulation error. I've written it there. Yeah, does that make sense? Like it's kind of like an RNN, right? You're like taking your action, you're sticking it into your model again and again and again. You're saying that's what you're going to do at test time anyways, right? So you're asking the long-term futures to be aligned. But it's not as simple as a standard one-step supervised learning. So why wouldn't I do this? Yeah.
If the state you predict is out distribution, then like how do you know what the real state is that you should be you take an action?
In this procedure?
Yeah.
So in this procedure, you know that like yeah, so let's say this was your true trajectory, right? And like let's say my current state of the model is that it predicts something like this, right? I know that like let's assume deterministic dynamics. I know that if I had like played those actions from those things, I should like this thing is OOD, but it shouldn't be. It should go back to like the corresponding time step state from my true trajectory, right? And so if you look at this loss function, right, This loss function is like maximizing the likelihood of the true states that you saw. So like you have full trajectories in your training set, right? And so this is not saying what's going to happen at inference time. It's just saying at training time, on the training actions, you should be close to the training states, right? It's still not going to deal with the issue of like compounding for like some new state like that. So, but the hope is that if I can align it for multi-step, then it'll be good at multi-step also. Okay. I know Sid knows the answer to this, but yeah. Are there why wouldn't we do this? Like what this seems great, right? Like we're optimizing the objective that we care about. Like that is the multi-step future, and I care about the multi-step future, not the one step. So why wouldn't I do that?
Mention this like that it is the walls because taking multi-step. Yeah,
How do you understand that one?
like the model will get very dependent on the reward functions.
You're still learning a one-step model. Like like earlier what I was saying is you're taking a state and a first action and a policy and predicting case steps in the future. Here we're still learning a one-step model, and you're still playing the actions to the one, like this objective is still learning a one-step model. It's just like using the one-step model recursively. So it's not quality dependent in that sense.
Have the same issue with the current limits.
Yeah, exactly. Right. So, exactly. So it's basically like, the problem is that it's like this, like, even for really simple one-step models, when you look at the multi-step objective, it becomes this like challenging, non-convex, like painful optimization because you're like feeding things back into the model. And it's often really hard to optimize that for. And so if you play around with it, you should do it, you should have this extra credit, but if you play around with it, you'll find that like often optimizing one-step loss is easy. Optimizing this multi-step losses, it just like doesn't do very well. The landscape is kind of nasty. And so you can try this, but it doesn't work great. Okay, does that make sense? Roughly. So like idea one is let's try to optimize one-step models on making sure that their multi-step recursive behavior is good. But that is hard for optimization reasons. Like it's hard to solve this non-convex. Idea two is kind of like what Kunal was alluding to earlier, is that we have this like model bias OOD problem. If I'm like hallucinating futures that are unreasonable, let me like predict when I'm unreasonable and account for it. And so essentially what that's saying is like, let's measure uncertainty. And if I can measure uncertainty and account for it, then I'm not going to hallucinate futures that don't exist. And so what that means is that, like essentially, let's say I had a model, this was the true model, and I had like many possible futures I could draw from the model, one of which is like pretty close to accurate, right? If I can estimate that these are actually unrealistic futures, I have high uncertainty on them, then I can like plan under the things that I'm certain about and not plan under the things that I'm not certain about. And so the idea is that we can try measuring uncertainty to go from something like a maximum likelihood model to an uncertainty aware model. So if I'm able to estimate like, this thing has no idea that it's just like, it thinks that its model is like mint ground truth. But an uncertainty aware model knows that like I'm in this place where I'm like not aware that or in this place that I'm aware that I don't know what the right answer is, right? And basically you can't ask your model to be good there. And so you can try and account for it in different ways. So the reason why this is different than like trajectory optimization is in like trajectory optimization, your model is good everywhere, or often it's good everywhere, as in it's a ground truth model. Whereas in a learned model, your model is not good everywhere. It's trained on some data. It may or may not be good in other places, right? And so what uncertainty aware models do is they like let your learned model account for where it's not good, and like your planning uses that to like not take hallucinated futures that are not good. Does that make sense? Like the idea is that these issues would not happen if you didn't have a learned model. Like it comes from the fact that the learned model is imperfect. Questions?
I mean, any more would be. Because it's a model.
Yes, although the type of imperfection of a learned model is a little different, right? Like often in a ground truth model, like there's some disturbances that are often modeled like IID. Whereas in a learned model, it like specifically gets worse the more you go out of distribution. Okay, so the idea here is that you want to model uncertainty and you want to propagate uncertainty, incorporate that into plan. Go check.
In practice, when you implement this, you predict uncertainty, but each dimension of like the state or.
Let me describe how we do that. Okay, so how do we model uncertainty, right? How do we do this tractably? So I guess we want to like quantify what uncertainty is, right? So there's different types of uncertainty you can think about. The first is aleatoric uncertainty. By aleatoric uncertainty, you mean uncertainty that is inherent to your environment, right? So saying that like, as we were saying earlier, like anything that you're not observing in your world will lead to stochastic outcomes. And that is inherent to your choice of state space and your environment, right? So like an example here is like, if you look at this data, like you can see that there's like some amount of variance in this data already. Like at this point, there's some amount of noise and variance, right? So that uncertainty, which is inherent to your data, is aleatoric uncertainty. And so it's like inherent to your environment. Or so inherent to your environment or inherent to your system. And then there's epistemic uncertainty, which is coming because of lack of data. That's just saying that like, this is inherent to even in the places that have data, there's like variance. And then epistemic uncertainty is saying there's areas where I don't have data. And in those areas, I don't know what to do. Right? And so aleatoric uncertainty is about the environment stochasticity, and epistemic uncertainty is about the lack of data. Right? And so aleatoric uncertainty is arguably like easier to solve. You just have a probabilistic model. But epistemic uncertainty is harder to solve because it's really, the model has to know what it doesn't know. Right? And it has to know that it doesn't know. And so often these things you can solve with like a diffusion model or a richer model class, like something that can capture noise. But epistemic uncertainty is harder to deal with because normally in most supervised learning problems, your model is like wildly overconfident. Like it thinks it's perfect even when it's not. Right? And so those are the two types of uncertainties we're going to deal with, and then we'll think about largely about epistemic uncertainty. Right? So the types of uncertainty we want to deal with, like we're going to assume that all of our models are probabilistic models. We're going to learn like a Gaussian or a mixture of Gaussians or something rich. But we haven't yet talked about how to measure uncertainty and capture it in our model. Epistemic uncertainty. So epistemic uncertainty being uncertainty from the lack of data. And when I mean from the lack of data, I mean that just given this data, the ones that are shown in these green X's, like there's many possible functions that could fit that data, right? So inherently you have to maintain uncertainty about what the functions are in between. And most neural net functions will like confidently do some crazy shit. And so we really want to be able to maintain that uncertainty so that I don't do that. Okay. So we want to get this epistemic uncertainty. We've kind of talked about one way to do this before. How do you do that? We want to understand uncertainty, but
Stagger or to kind of plug that in ambiguously. Then we can do that kind of here as well. Whereas like if we go out distribution somewhere where we label and collect more data.
So Dagger can certainly help, but let's say we didn't have, no one is giving us more data. It's more that I need to estimate where I know things and where I don't know things, or where I have data, I don't have data. So it's more like, let's say I was given this and I was given this, or let's say in a model-based RL case, I was given some data here, and someone is asking me, like, do you know what to do here? Like, how do I change my model to estimate that? But the reparameterization trick is a good way to like pass gradients through stochastic optimization, but it's still optimizing some maximum likelihood objective, which means that it's like maximizing the likelihood, pretending that your model was the true model. Yeah.
Maybe just run a bunch of models,
That's
and then see when they disagree, then probably it's.
Exactly. It's like basically a bunch of the groups talked about this in our seated discussion. But an ensemble method is a good way of measuring epistemic uncertainty because the models agree here and the models disagree here. But before we go to ensembles, let's try and think of like a different way of doing this, which is the Bayesian way of doing this, right? So the idea here is that given a data set, right, you can kind of think of theta as your parameter. This is not specific to model-based RL. This is more generally. If I have some data set D and some parameter theta, you can think of like theta as something that takes in, it's like parameterizes the function that takes in x and gives you y in any prediction problem. And as we saw earlier, let's say you had like some amount of data here, some amount of data here. You had the sinusoid function, right? Given this data, you can reduce your class of functions. You can say that things that are not consistent with this class of functions are like unlikely to be the true function, but you can't reduce it to a singleton set. Like instead, what you have is you have a likelihood over what the parameters are that are consistent with the data. So what that means is that rather than saying that, let's say you have this data and this data, rather than saying that like, this is the true function. So what supervised learning would do is it says, you have this data, you maximize likelihood. So you try to pick the maximum likelihood function and you say like, that is the ground truth. Right? The Bayesian view on things says is that there is a distribution of what functions are consistent with the data. And so it says that there are many, like all of the functions are consistent with the training data, right? But they might vary in between, right? And you really want to maintain a distribution over what models are consistent with the data. Okay, so why is this uncertainty? Because it's telling me that like I find a distribution of models that are consistent with the data, and I see where those models disagree, and that kind of tells me like how high variance, like what my uncertainty is, right? So this is often called your posterior, right? So you often think of P of y given x and theta as your likelihood, right? You think of P of theta given xy as your posterior. So this is, for those of you familiar with Bayesian optimization, Bayesian modeling, like this is your likelihood, this is your posterior. And the problem of epistemic uncertainty modeling is a similar problem to the problem of modeling your posterior. Okay, so what we really want to do is we want to estimate this posterior. Like, let's say you're given some SAS prime data, right? Like let's say you're given a data set of SAS prime. You want to like estimate your theta given SAS prime. Okay, because it's telling you what set of models are consistent with the data that you saw. Right? So like I find it useful to think about this graphically. It's like saying that this is the data that you saw. Like give me let's say the shading tells me how likely the functions are. Like give me a shading over all the possible functions that are like consistent with my data. And so that's kind of what my posterior is trying to represent. It's trying to represent a distribution over functions which are consistent with the data. Okay, and so I think people are a bit lost. They'll like ask me questions. Or does this not make sense at all? We should start again. Or does this make complete sense? Yeah.
Why are we taking this approach to estimating variance? Like, is there no inherent variance in these?
So there is, so this is like, when you say there's no inherent variance to your posterior, I guess what this is trying to do is it's trying to measure like, it's trying to measure like this. Right, so it's basically saying that if I can measure the distribution over functions that are consistent with the data, then I can like query, like what I can do is at any new query point, I sample from my distribution of functions. I see how different their values are, and that tells me what the variance is going to be. Right? But I need to get a distribution of functions that are consistent with the data. And then the point is like, I need like, if I don't do that, and I do what maximum likelihood does, like the type of one-step model we learned, then you like only have a point estimate which thinks it's perfectly accurate. Right? And so I guess the way I was going to kind of go about this was to talk about the general scheme of learning posteriors and then showing that the ensemble methods are an approximation to posteriors.
I guess this is cool, but I have like a simple idea on this last one.
Yeah.
So we want to know what we're like out of this. Why don't we just give whatever we're trying to take as close to our existing data?
Yeah, so the close under what method?
That's, I guess, yeah, that's like the question. You could just take a Euclidean distance or something.
So then if, like, let's say you're going to images or something, and you're in trouble.
Yeah.
So that's generally a pretty reasonable approach, like a nearest neighbor type approach, but it's hard to do from high dimensional spaces. And when you don't know the metric.
Tracers also do that like that, they characterize your model. And if like each data parameter vary,
Mhm.
like how you just get a reasonable output.
So the way that we're going to actually parameterize these things is like we think of like our forward model, which is S prime given S and A, as parameterized by theta. Like theta determines like how do I make a prediction from SA to S prime. And the way like maybe let's do the next animation will help us here. But the way I'm going to like parameterize this thing is by Bayes rule. This thing is Bayes rule. Right? Bayes rule says that P of like x given y is P of y given x, P of x, divided by P of y. Okay? And so this is just Bayes rule. I'm sorry, my x's and y's look the same. So one way, like to make this super concrete, like what P of D given theta would be is going to be P of S prime given S A theta. What P of theta is going to be, it's going to be some prior over function that you have. It's a uniform. And then you're going to like integrate this thingy over all possible functions. Okay? And so like the way that you have to estimate this is like your likelihood function from your neural net, like your forward model. This is just like a uniform distribution over parameters or something like that. And then you have like to compute the posterior, you have to like essentially weight, you have to multiply P of S prime SA theta by the likelihood, and then normalize it by the integral over all functions. Right, so to like properly get a posterior, you have to like solve this problem, which is like Bayesian approximation or Bayesian estimation, or Bayesian inference. And Bayesian inference is hard because the denominator is really hard to compute. Because you have to like integrate, what this means is I have to integrate over all functions. So if I wanted to like get a proper estimate to uncertainty, epistemic uncertainty, I have to integrate over all parameters. That is very hard to do. And so there's like lots of approximations that people use, but all of them are like essentially trying to like approximate the posterior. Right, so the Thomas's question from before, what we're like essentially what we're trying to do is if we can model P of theta given E, then we can model how different models behave in out of distribution data. We just find it hard to approximate that directly because of this Bayesian like denominator problem. And so everything else we're going to discuss after this is an approximation to this posterior. Okay, we have let me tell you the,
Yeah, quick question. I think, a lot of people's minds immediately go to Gaussian processes. Why not Gaussian processes?
So a lot of the really successful model-based RL methods do Gaussian processes, which is like a non-parametric way of getting uncertainty estimates, right? The challenge with Gaussian processes is that they don't, because they're non-parametric, they don't scale that well with data, and they don't scale as well with dimensionality. Right? So if you're going from images and so on.
And like, because folks brought it up yesterday, like the other day when we talked about some, like just having a nice expressive model with lots of dropouts.
Yeah.
Would that be a
Yeah. So that's like the next thing we're talking about. Which is learning an ensemble of models or learning dropout is often a really effective approximation that we're going to use in a bunch of ways. So I guess my point is we want to learn the posterior. that's what we care about for epistemic uncertainty. The posterior is hard to approximate because the denominator being an integral over all models. We're going to instead approximate it. This thing is like, this is a fancy way of doing it in variational inference, but the easy way to do it, and the way that most people will do it, is just learning an ensemble of models or doing dropout. And so just as we did for TD3, you learn an ensemble of models, and you argue that in places where you don't see much data, the models disagree. And so that you can show that it's an approximate posterior. It's approximate, like if you have infinitely many models, and you do this properly, then you can show that it's the true posterior. But when you have a finite number of ensembles, and you're like often initializing them, like having the same architecture for them, then it's like an approximation, right? So the point is that if I want to estimate uncertainty, the idea is you can have an ensemble of models that train on the same data. And in places where you have data, the models agree. In places where you don't have data, the models don't agree, right? And so if you go back to our example from earlier, it's saying that like in these regions, the models will all agree. And in these, because you're training data there, in these regions, because the models are initialized differently, maybe see different data, they will disagree, right? And so then you can look at the variance in your ensemble predictions as an approximation to epistemic uncertainty. And so the thought here is that learn in ensembles, look at the variance, use that to measure uncertainty, and we'll talk about how to use this in planning next. Right. Any questions before we end? Yeah.
Methods typically not work well compared to the ensemble.
Use the MCMC methods.
Do you typically not work well?
Often MCMC methods are used. We have to like, get them to mix the chains to mix. And ensembles work unreasonably well. And so I think it's just like easier and more scale. But MCMC is like a good way to think. Okay, awesome. Thank you guys. See you, I guess Monday's a holiday. See you next Wednesday. Veterans Day, I think. Yeah.
Needed.
Yes.